Good morning, class. Today's video will focus on this last rule, the derivative of an exponential function. In many ways, this is the simplest of the rules on this sheet because when you take the derivative of e to the u, it is e to the u, the exact same exponential function. You simply have to multiply by the derivative of the exponent u itself. Okay, so e to the u multiplied by the derivative of u. As you might imagine, I'm going to be mixing this rule in with all of these other ones we've already studied so that we get some strange variations. We will probably encounter some composition of functions as well as chain rule, product rule, quotient rule. Okay, so let's have a look at the examples I've selected for today. So we start right here, y equals 4 times e to the 3x. So in forming y prime, the constant 4 remains out front, and then we multiply it by the derivative of e to the 3x. And its derivative is e to the 3x times the derivative of 3x, which is 3. Okay, so 3x is like the little u in e to the u, and its derivative is e to the u times the derivative of u. So here we get 12 e to the 3x. Okay, taking a look at the second one, this is a similar example, except we would not begin with this function in the denominator. We would first rewrite the function y like this with a negative exponent. And now we could apply our derivative rule. This now is the u in e to the u. And that means the derivative will be 3 e to the negative 6x multiplied by the derivative of negative 6x, which is negative 6. So we now have negative 18 e to the negative 6x as y prime. And this, of course, can be written with a positive exponent like this. So we have negative 18 over e to the 6x. All right. So we would have rewritten the function y even if this was just 3 over x squared. Then before differentiating, we would have written it 3 times x to the negative 2. And then we would have used our derivative rules, okay? So this is just a similar example. We don't leave the variable in the denominator. We first write it with a negative exponent, then we can form the derivative. Okay, let's look at the next question, problem 3. We certainly have a function of the form e to the u. So in forming its derivative, we write e to the u, and this has to be multiplied by the derivative of u. So we need to know what is the derivative of sine 4x. So if you don't remember, you can look at your sheet. The derivative of sine u is cos u times the derivative of u. So if we have sine 4x, its derivative is cos 4x times 4. So that's what goes here, cos 4x times 4. Okay, so this portion here corresponds to the derivative of u with respect to x. And so in rewriting the answer, the important part here is that the coefficient would be in the front. So 4 would be first. And then it doesn't matter if you write the exponential function next or the cosine function. That's up to you. So I'm going to choose to write the cosine function first and then the exponential function like that. But the key is natural expression of this term would have the coefficient in the front. All right, so those ones, take a look. We had functions of the form e to the u in each case, and we differentiated. Now, let's have a look at number 4. The exponential function is part of the binomial. The binomial is cubed. So we could proceed in a couple of different ways. One way is to actually cube this binomial, but that's going to require me either to know the formula for cubing a binomial, which some of you might know, or to do some pretty heavy-duty algebra. And in fact, we don't have to do that. We don't have to first expand this. If we simply use the chain rule when forming y prime. So if we want to use the chain rule, remember you start with the exponent. So the exponent comes forward. The new exponent will be 2. The inside of the bracket remains as it was. And then we need to multiply that by the derivative of the inside of the bracket. So the chain rule always works like this. If this was just something algebraic in here, like 5x plus 1, then this would say 3 5x plus 1 squared. And then we would be multiplying now by the derivative of 5x plus 1. So the chain rule always works just like this. So you do the exponent business first, keeping the inside the same, and then you just have to multiply by the derivative of the inside of the bracket. So what is the derivative of e to the 2x plus 1? Well, first we write down the derivative of e to the 2x, and that's simply going to be e to the 2x times 2. And that would be added to the derivative of 1, but the derivative of 1 is 0. Okay, so I'll just show it to you like this so that it applies in general a little bit better, right? If this is a binomial, we would just write the derivative of the first term plus the derivative of the second term, and that would generally be in a bracket. But in this case, this part is 0. All right, so now all we do is put this all together. So this is 2e to the 2x multiplied by 3. So that's 6e to the 2x. And then we have the square of 2x plus 1, like that. So that's our final result. Okay, let's have a look at the next example. Okay, so here we go. This is example 5. We have e to the 2 theta. So theta is now the independent variable. So everywhere here where you see an x, you must consider it to be theta. So we're taking the derivative with respect to theta. We have e to the 2 theta times the ln of the cosine of theta. Now look, that independent variable is in 2 places. And right here, between the exponential function and the logarithm, of course, multiplication is implied. And so what does this mean? This means we're going to have to use a product rule. Now, in using the product rule, the exponential function is the u. So I'm going to do an uppercase u. And so that means this logarithmic function is the v. So we have to begin by forming both u prime and v prime. So I think that u prime is quite straightforward. What's the derivative of e to the 2 theta? Well, it's e to the 2 theta times 2, or 2e to the 2 theta. Okay, that's our new derivative rule for today, the 8th one on the list. Now, what about forming the derivative of v? So this is the ln of cos theta. So take a look at number 7, the ln of u, little u now, the argument of the logarithm. So this means cos theta is the little u. It's the argument of the logarithm. So how do you form the derivative of ln u? It has two parts, 1 over u times the derivative of u. Now this will be with respect to theta. So two parts, 1 over u times the derivative of u. Okay, here's u. So the first part, 1 over u, will look like that. So that's the 1 over u part, and now I need to multiply that by the derivative of u with respect to theta. That means, what is the derivative of cos theta? Well, the derivative of cos theta is negative sine theta, and this would be times the derivative of theta with respect to theta. So this part is just 1. So what's the derivative of cos theta? It's negative sine theta. There we go. So again, those are the two required portions for our rule. This part right here is the 1 over u part. I was just wondering where to put my little markings. If you like to have little markings, that's the 1 over u part. And this part here is the derivative of u with respect to theta. Okay, but what is this equal to? This is the same as negative sine theta over cos theta. Negative sine theta over cos theta. All right, negative sine theta over cos theta is what we have now. And sine over cosine is tangent. So this is negative tangent theta. Just like that. All right, so now I'm all set because I have u and v, u prime and v prime, so I'm going to use the product rule to form y prime. So product rule, if you forget it, it's here. uv prime plus vu prime. Okay, so u times v prime plus v times u prime. Okay, now this is all one term, and remember the coefficient should precede the term. It should be at the beginning of the term. So this is the same as negative e to the 2 theta tan theta. Okay, same thing here. After the plus sign, the coefficient should be first. So the 2 should be first. And then whether you want to have the logarithm or the exponential next is up to you. Okay, but absolutely, coefficient is the first thing in the term. And now this one is kind of screaming at me to common factor e to the 2 theta. So I'll do that to finish. E to the 2 theta is removed as common from each of these terms. So from this term, we'll just be left with negative tan theta. Then we'll have the plus sign, the number 2, and the logarithm. Okay? And if you were to open this up using multiplication, of course you would get this previous line back. And that's perfect like that. In here, if you want to write the positive term first, so this is more common, would be to have that minus that. But they're both correct. This is correct, this is correct. Okay? All right, so there we go. That was a fifth example. Now let's contrast that with number 6. We have the ln of x squared e to the x. So while this problem overall, right here, was considered a product, this one overall is just considered a logarithm because all of this is now the little u for ln u. Okay. So this dictates how we begin the problem. We don't begin with a product rule like we did here, but rather we begin with what is the derivative of ln u? Well, remember it has two parts. First is the 1 over u part. And then that should be multiplied by the derivative of u. So I'm going to just write here that here's where we would be multiplying by the derivative of little u. In other words, the derivative of x squared e to the x would be here. Okay, so another way to write that, if you don't want to write it like this, I'm just going to show you some options. Right here, we need the derivative of this. Okay, so those two things were equivalent. But it definitely starts like this with the 1 over u times, now right here in this place, we need the derivative of this. Well, now here's the interesting part. How do you form the derivative of this? Well, it is two functions of x multiplied together, which means it's a product. That's u and that's v. So this time, the product is in the argument of the function. So in this spot here, we definitely need a product rule. So let's write down what we're going to use for u prime and v prime. I think I have room here because they're very simple derivatives. Okay, so firstly, what's the derivative of capital U, which is x squared? It is 2x. What's the derivative of e to the x? It is e to the x times the derivative of x, or e to the x times 1. So it's simply e to the x. So now I still have this portion in the front. That's 1 over u. Oops, I think I just broke my correction tape. Oh my Lord, I did. Just split apart. Oh, here, should I show you? Look what just happened to my correction tape. Oh my goodness, it's in pieces. Oh, this is a lot of pressure now. Do you know what this means? This means I cannot make any more mistakes. And it also means I may have to try to fix this later or go shopping. Okay, only when I'm out anyway, getting my stuff from the drugstore, right? No extra trips shopping. Even though Christmas is coming up, we need to keep everybody safe. Okay, that was a big departure from the lesson. I'm sorry. Here we go, back to this, okay? So we have the 1 over u, and now we're gonna do the derivative of the argument u. We just decided it's going to require a product rule. Now, the product rule by its very nature is a binomial, right? Two terms separated by a plus sign, and that means I definitely need a bracket here, okay? So here we go, u times v prime plus v times u prime, just like that. So 1 over u, and this is the derivative of the argument u. Okay, but this is the same as having this in the numerator. So in the numerator now I have x squared e to the x plus, in this term, put the coefficient first. So the 2 first. Then it doesn't matter whether you put the x or the e to the x. That's up to you. But definitely the 2 in front. Okay, like that. Underneath is this. Okay. So numerator, denominator. But that numerator should be factored. So from each term, we can common factor an e to the x. And from each term, we can common factor an x. So I'm going to take out x, e to the x. From this term, that will leave x plus, and from this term, we'll have just a 2. Okay, so that's the numerator, common factored, and now look, we can reduce this. So e to the x cancels, but not only that, we can cancel an x from the top and the bottom. Final answer then, x plus 2 over x. So that's a very nice simplified answer for the derivative of the ln of x squared multiplied by e to the x. Okay, so overall, this was a product. Here, overall, this is just a logarithmic function whose argument is a product. Okay, we're gonna do a couple more here. This one. Yes, it looks like there is a product in the denominator and that overall this is a quotient. But that would be a nightmare to differentiate. In fact, we can simplify this just using the laws of exponents. Let me show you. In the denominator, the two exponential functions are multiplied together. It's the same as powers having the same base. The base is e. So what do you do when you multiply powers of the same base? You simply add the exponents. So this is the same as e to the x plus 3x, which is 4x. It's 1x plus 3x, so 4x. And now we can take this even further. I don't want to do a quotient rule on this, and I certainly don't have to, because this is now division of powers with the same base. And to simplify that, we simply subtract exponents. So this is 2 times e to the 6x minus 4x, which is 2x. So the original function is the same as this function. And now the derivative is super simple. The 2 stays, and we multiply by the derivative of e to the 2x, which is e to the 2x times 2. The derivative of e to the u is e to the u times the derivative of u. So 4 e to the 2x is the derivative. That one was pretty nice since we were able to use our exponent rules. Okay, last one. This one's less nice. This will be many, many steps, but at least it's the last one, okay? Look, e to the 2x times the sine of 3 pi x. The x is the independent variable. It's in 2 different spots. Implied is multiplication. So overall, the original function f at x is a product. So we're going to use the product rule to find f prime at x. But look at this. Find f double prime at 0. This means we're going to be finding the second derivative. Okay, but let's start with our first derivative. So this is our capital U, and this is our capital V. What will we use for U prime? The derivative of e to the 2x is 2e to the 2x. Now we need the derivative of v prime. V is the sine of 3 pi x. So this is the little u in sine u. What's the derivative of sine u? It's cos u times the derivative of u. So cos u times the derivative of 3 pi x. What's the derivative of 3 pi x? It's 3 pi times 1. So it's just 3 pi. And so we should write this with the coefficient in front. 3 pi times the cosine of 3 pi x is correct for v prime. Okay, so now f prime at x. U times v prime plus v times u prime, like that. Okay, now that's not too bad, except when I remember that I'm going to be finding the derivative again, and this is a product, and so is this, I might be better off removing e to the 2x as common here. Right? Because it's here and here, it's in both terms. So take e to the 2x out, and now we have 3 pi cos 3 pi x plus, so e to the 2x is out. That leaves me with this. I know that I write the 2 in front because it's the coefficient. Okay? If you were to open this up using multiplication, you'd get the previous line back. Okay, there we go. So that's the first derivative, and it's been common factored. Now I'm going to be finding the second derivative. So this will be my capital U. That's one function of x, and this sum is the capital V. So before I use the product rule again to find the second derivative, I take note it's the same u as before, and therefore it's the same u prime. But v prime, of course, is different. So let's work out our new v prime. If you just want to write down u prime again, certainly that doesn't hurt. Okay, so I'm going to do the new v prime. So we have 3 pi multiplied by the derivative of cosine 3 pi x. I'm going to need more space. Oh, see, this is when I need my correction tape, but I'm right out of luck on that regard. I'm just going to write super small. I have to commit to this now. Okay, so can you believe I only have one at home? If I were at my office, of course, I'd have access to a supply cupboard, but anyway. So 3 pi gets multiplied by the derivative of cosine 3 pi x. Its derivative is negative sine 3 pi x times 3 pi. So negative 3 pi sine 3 pi x, like that. So this constant is in front. The derivative of cosine 3 pi x is here. Now I'm at the plus sign, and I have 2 already, and it has to be multiplied by the derivative of sine 3 pi x. And we already differentiated sine 3 pi x here. It's 3 pi, so times 3 pi cos 3 pi x. Sorry, that got tiny. Hopefully you can zoom in here as required. So 3 pi is multiplied by this derivative of cos 3 pi x. Then we have plus 2, and it's multiplied by the derivative of sine 3 pi x, which is right here, 3 pi cos 3 pi x. So if v is a sum, then v prime is also a sum. But let's write that properly now. So this will be negative 9 pi squared sine of 3 pi x plus 6 pi cos 3 pi x. So that's my v prime, if you can believe it. Okay, now we have everything we need. U prime, v prime. So let's do this. F double prime at x is, so we go u times v prime okay, so that's u v prime plus, I'm going to go to the next line, plus v is this whole thing, uv prime plus v times u prime. And certainly we could try common factoring again and so on. But look, we actually want to evaluate this when x is 0. So I am going to take advantage of that. I'm going to come through now and substitute 0 wherever there is an x. So look what that's, e to the 2 times 0. So e to the 0. Negative 9 pi squared sine of 3 pi times 0, okay, plus 6 pi cosine of 3 pi times 0, plus, and here we get 3 pi cos 0, plus 2 sine 0, times 2 e to the 0. Okay, so I've gone and substituted 0 wherever there was an x, and now we can evaluate these things. E to the 0 is just 1. Now, the sine of 0 is 0, so this whole term is 0. Plus, the cosine of 0 is 1, so this is now 6 pi times 1. Okay, and now we have this, plus. So this is 2 times 1, e to the 0 is 1. So 2 times 1, which I think I'll put in front of the bracket instead of at the end of the bracket, coefficients in front. And in here, 3 pi times 1, because again, cosine of 0 is 1, plus 2 times 0, like that. Okay, and if you didn't know sine of 0 is 0, just make sure you're, well, actually it doesn't matter when it's a 0, but in general, for this whole test, you want your calculator to be in radians. So there should be a little tiny r there. Okay, and then you would just do sine of 0 is 0. And you could do cosine of 0 is, right? Okay. E to the 0, every base with an exponent of 0 is always 1, right? And that's certainly true of e to the 0 as well. Okay, so what do we got here? Anyway, we got 1 times 6 pi, so that's 6 pi, plus 2 times 3 pi, so that's another 6 pi, and we got 12 pi. And that was a very long question, so I apologize. But there you have it. That was 8 examples, largely using this rule. But as I promised, we had much fun because we mixed in all kinds of other things, including an identity, some of these other transcendental functions, and we didn't use a quotient rule. So there you go. At least I was kind in that regard, but we did use chain rule, product rule. Okay, thanks a lot. Please try the recommended problems. We have but one more video left in this course, so I will present that later this week. Thank you. Bye-bye.